Good morning. In this lecture onwards, we will discuss the last unit of our syllabus, the stellar astronomy. The topics which we will cover in this unit are about the distances, the unit of distances used in the astronomy, also about the brightness of the stars, how we can represent the brightness of a star, and apparent brightness or apparent magnitude and absolute magnitude of a star, etc. we will discuss under the topic brightness. Then we will discuss about the different categories of stars, how we can categorize the stars based on their brightness and the formation or the life cycle. Then after we will discuss about the life cycle or the formation of the star and its evolution. Evolution means during a life cycle what happens to the star. So these are the things which we will discuss in this topic. So the most important one is the distance, because if you consider the distant object and a near object, you can see that the near object may appear as brightest than the others because of its distance variations. So we will try to focus on the aspect, the distance of the star in this lecture. When we consider the astronomical distances, distance is the most important and difficult quantity to measure in astronomy. The reason for it to being the most important physical quantity in astronomy is the distance is that in order to estimate the total energy emitted by an object, we need the information regarding the distance. The total energy emitted by an object is called the luminosity. So to determine the luminosity of an object, we need an information regarding the distance of the object. Also, to calculate or to estimate the masses of the celestial objects from their orbital motions, we need the information regarding the distance of that object. Also, to estimate the motions through space of stars, we need its distance from Earth. The motions through space of stars means if we are considering the periodic motion, we need the period etc. to calculate the distance. So period and different aspects of the motions, we need the information about the distance of that object. Also, to discuss about the physical size of an object, we need the information regarding the distance of an object. As you consider in a full moon, the size of the moon, and in that day the size of the sun will appear almost same to us, but you know that moon is very much smaller than Earth, and sun is actually 100 times bigger than the size of Earth. So when you compare the size of moon and sun, sun is very big and the moon is very small object, but to us it appears that the moon and sun are comparable sizes. The reason is that moon is very near to us compared to the distance of the sun from us. So the distance of the objects will make to estimate will make a important quantity in the case of estimating the physical size of the object. These are the things which makes the distance measurement is the one of the most important part of the astronomy. I told you in the beginning that it is most important, at the same time it is the difficult quantity to measure in astronomy. The difficulty lies in the fact that the measurement of distances of something that is beyond the reach of a measuring instrument is very difficult. If you consider the distance of a star from us, we cannot have any instrument which reaches from Earth to that star. So if we are having an instrument whose reach is beyond our object's position, is not beyond our object's position, it is difficult to measure the distance. So that's why it makes all astronomy celestial objects are very far away, and there is no instrument which reaches from Earth to that celestial object. So that makes it very difficult to measure the distance in astronomy. Anyway, to estimate the luminosity, to estimate the mass of the object, to estimate the motions of the stars through space, and to estimate the physical size of the object, we need the measurement of distance. So in that case, that is, if the measuring distances are of something that is beyond the reach of measuring instrument, we will use the geometry to estimate the distance or to calculate the distance. Usually the method of trigonometric parallax is used as the direct geometric method of finding the distances. When we consider the distance, we know that meters and kilometers are the units which we are used on Earth. Sometimes we will use millimeters of distances, or centimeters of meters, or we will use meters, or sometimes we use kilometers, sometimes we will use miles to discuss the unit on the surface, to discuss the distances on the surface of Earth. But when we consider the astronomical distances, these distances are very small, these units are very small compared to the distance which we are going to discuss. So the two units which we commonly use in astronomy are, which is called parallax second, which is usually called as parsec, denoted by PC, and the light year. So these are the two units of astronomical distances used in astronomy. I told you the method of trigonometric parallax is the direct geometric method of finding the distance. So what is parallax actually? If you consider a nearby stars, they will appear to move with respect to more distant background stars due to the motion of the Earth around the Sun. This apparent motion is called the stellar parallax. To understand it, let's consider a geometrical diagram in which Sun is at this position and the Earth is revolving around the Sun. Suppose during June, Earth is at this point. This is during June. After 6 months, Earth will reach on diametrically other end of this point, that is, it will reach at this point. The Earth will reach at this point after 6 months, that is during December. This is I am assuming. During June, the Earth is at this position. After 6 months, the Earth will be at this position. Suppose I have a star at this point. Now, this is the line joining the star and sun, and this is the line of sight of Earth and star during June, and this is the line of sight of star during December from Earth. Now, when you observe the star during June and December, you can see that due to the motion of the Earth, you can see that the star has been moved at this much of angular distance. This is the angular distance moved by the star due to the apparent motion of the Earth, due to the motion of the Earth, and which is an apparent angular distance. Now, if you consider the half of this angle, actually these two lines make same angle with respect to this one. So, this will be the half of this angle, which is called the parallax angle, P, denoted by P. So, the parallax is the apparent motion of a star due to the Earth's rotation around the sun, which appears that a star moves with respect to more distant background stars due to the motion of the Earth. This motion is called stellar parallax. So, the apparent motion in which a star appears to move with respect to the distant background stars due to the motion of the Earth around sun is called parallax or stellar parallax. Now, in the above picture, we have seen that the line of sight to the star in December is different from that in June, when the Earth is on the other side of the orbit. As seen from the Earth, nearby star appear to seep through an angle shown, which is denoted by the parallax angle small p. Now, from the previous diagram, you can see that as the distance of the star increases, the star is here, then the parallax angle will be this much. It will be smaller than this value. So, if you call it as p prime and it is p double prime, suppose star is at this point, then you can have like an angle like this, it is p double prime. So, you can see that p prime is greater than p double prime is greater than p triple prime. That is, as the distance of the star increases, the parallax angle decreases. Now, if you consider the nearest stars, which are very far away, the largest measured parallax is very small and it is less than an arc second. If you consider the nearest star Proxima Centauri from Earth other than Sun, which has a parallax of 0.772 arc second, which is the largest parallax observed for any star. So, 0.772 arc second is the largest parallax observed for any star, which is for the Proxima Centauri, the nearest star to Earth other than Sun. So, which is less than 1 arc second. Now, If we consider the first parallax, which is observed in 1837 by Frederick Bessel for the star 61 Cygni. Today we use different photographic and digital imaging techniques to measure the parallax. Also, we measure the parallaxes from the space to avoid the blurring due to the Earth's atmosphere. So, based on this, you can form a fundamental unit for the distance in astronomy, that is, the direct thing which we can measure is the parallax angle. So, from parallax angle P, you can form a distance relation just by considering that this d is inversely proportional to P. That is, as distance increases, the parallax angle increases, or as distance increases, the parallax angle decreases, or the parallax as the parallax angle increases, the distance decreases. That we can put in the form of an equation which is given by d is equal to 1 by P. That is, we directly convert that observed parallax angle to the distance by using the formula d is equal to 1 by P, where the condition is that the P is the parallax angle in seconds. Then this d will be the distance in parsec, which is one of the unit used to represent the distances in astronomy. So, which is called the parallax second, or if you consider this parallax second, first three letters of parallax is PAR, par, and the first three letters of second is SEC. So, together we can have parsec, which is usually denoted by PC. Writing our parallax formula in this way allows us to define a new natural unit for distance in astronomy, the parallax second or parsec. So, parallax second or parsec is the natural unit of distance in astronomy. It is called natural because of it is directly obtained from the measured parallax angle. So, it is treated to be the fundamental unit of distance in astronomy. So, parallax second or parsec is the fundamental unit of distance in astronomy. Now, if you consider the relation d is equal to 1 by P, where P is the parallax angle in second. Suppose for a star P is equal to 1 second, you know that for any non-star P is always less than 1. The nearest star Proxima Centauri is having a parallax of 0.772. But to define 1 parsec, I am considering the condition that P is equal to 1 arc second, then which leads the fact that d is equal to 1 parsec, 1 PC. So, from here we can define 1 parsec as the distance of a star which has a parallax of 1 arc second, or we can say that a star with a parallax of 1 arc second has a distance of 1 parsec. So, this is the way we can define 1 parsec. Now, if we can try to convert how we can convert this parsec into the non-units, that is in terms of the meters or astronomical unit. Astronomical unit is another fundamental unit which we are used in astronomy, especially in the to measure the distances in solar system. So, stars are beyond our solar system. That's why we are using the parsec to represent the distances in astronomy. So let's see how we can convert it. From the previous geometrical diagram, we have constituted a diagram like this. The earth is at one point, the sun is another point, and the star is at another point. These three system forms a triangular pattern. Now this is the distance d, that is earth and star is at a distance of d, sun and earth is at a distance of 1 astronomical unit, and this angle is the parallax p, small p. And we know the relation d is equal to 1 by p. Before that, using this triangle, I am considering the equation sin p is equal to 1 astronomical unit by d, that is opposite side by hypotenuse. Sine of an angle is the opposite side by hypotenuse. So here sin p is equal to 1 astronomical unit divided by d. Now you know that p is very small, so sin p can be treated to be approximately equal to p. So p is equal to 1 astronomical unit divided by d. Now we want the expression for d. So d is equal to 1 AU divided by p, which is equal to 1 AU divided by p is, let's hope it to be in seconds, then it is p. If p is in arc seconds, then d is in parsec, pc. So we need to define what is 1 pc. So to define 1 d is equal to 1 pc, we have seen that d is 1 pc when p is equal to 1 arc second. So put p is equal to 1 arc second in this equation. In this equation, we will get d as 1 pc is equal to 1 astronomical unit divided by 1 arc second. Now we will convert this 1 arc second to its radians. Then 1 arc second is actually, to convert it into radian, I will consider how we can consider this angle into radian. You know that 360 degrees is 2 pi. From this you will get 1 degree is equal to pi by 180, but 1 degree is equal to 60 minutes. So 60 minutes is equal to pi by 180. So 1 minute will be pi by 180 into 60 radians. So this will be equal to 60 seconds. So 1 minute is 60 seconds. So 1 second will be, from this equation, it will be pi divided by 180 into 60 radians. Now this value, if you do, it will be 1 by 2,06,265. That is 1 second. So 1 second is equal to 1 by 2,06,265 radians. So if we can put it here, you will get 1 pc is equal to 1 astronomical unit divided by 1 by 206,265. So it is 206,265 astronomical units. So 1 parsec is equal to 2,06,265 astronomical unit. Now that will be equal to 3.26 light years. In the initial or beginning I told you that another unit of distance in astronomy is the light year. We will define what light year is in the next after few time. So just remember that 1 pc is equal to 3.26 light years. How this conversion has been brought about will be discussed after discussing what light years is. Now you know that 1 pc is equal to 206 265 astronomical unit, but one astronomical unit is 1.49 into 10 raised to 11. If you do this calculation, you can see that it will be 3.086 into 10 raised to 16 meters. So 1 parsec in meter, it will be 3.086 into 10 raised to 16 meters. So that is the conversion of parsec from parsec to other used distances, that is astronomical unit, light years and meters. Now the another unit of distance, which we call it as the light year, which is defined as the distance of light travelled in 1 year. So the light year is an alternative unit of astronomical distances used in astronomy. So a light year is the distance travelled by the light in 1 year. So to calculate it, let's consider 1 light year is the distance of light travelled in 1 year. If you consider the velocity of light, it is 3 into 10 raised to 8 meter per second. That means light travels 3 into 10 raised to 8 meters in 1 second. So we have to convert this into the year, that is 60 seconds is 1 minute. So 3 into 10 raised to 8 into 60 will give you the distance travelled by the light in 1 minute. If you multiply, converts minutes into hours, then we have to multiply it by 60. So this value gives the distance of light travelled in 1 hour. So if you multiply it by 24, we will get the distance of light travelled in 1 day. If you multiply it by 365, we will get distance of distance travelled by the light in 1 year. So if you do this calculation, you will get the value as 9.4608 into 10 raised to 15 meters. Here you will have a meter. So 1 light year is equal to 9.4608 into 10 raised to 15 meters. But in the previous slide we have discussed 1 pc is equal to 3.086 into 10 raised to 16 meters. So if you divide it by this equation, that is 1 light year is equal to 9.4608 into 10 raised to 15 meters. Divide these two equations, you will get 1 light year by 1 pc is equal to 9.4608 into 10 raised to 15 divided by 3.086 into 10 raised to 16. So this value will be 1 light year will be equal to 0.31 pc. If you do this calculation, 9.4608 into 10 raised to 15 divided by 3.086 into 10 raised to 16, it will come around 0.31. So 1 light year is equal to 0.31 pc or parsec. Or from this equation you can have 1 pc is equal to 1 by 0.31 light year, so which will be 3.26 light year. This is the conversion which we have seen in the previous one. Also, if you consider this, convert this light year into astronomical unit, that is, if you divide this equation by 1.49 into 10 raised to 11, you will get 1 light year in astronomical unit, that is 63,270 astronomical unit. So this is the way we can have the light year. So far we have seen that the astronomical distance in stellar astronomy can be represented by using either parsec or light year, but light year is actually used up by the writers of popular science books and science fiction writers. When we consider the research astronomy, this unit, that is light year, is rarely used. The reason is that parsec is directly derived from the quantity that is being measured, whereas light year must be derived from having previously measured distance in parsec. That is, if you consider the method of measurement of distances of a star in stellar astronomy, it is directly obtained from the parallax angle measured for that star. If you are having the parallax angle measured, then the direct distance directly obtained from that parallax angle is in parsec. So the researchers will use parsec as the most fundamental unit of distance in stellar astronomy. So that is why the researchers use this unit as the distance in stellar astronomy. So now if you consider the star Alpha Centaurea, which has a parallax of 0.742 hours second, then the distance of this star is 1 by p, that is 1 by 0.742, which is equal to 1.35 parsec. So 1.35 parsec means you have to multiply it by 3.086 into 10 raised to 16 meters to get the distance in meter. So that is way we can convert these distances. Now you know that the stars are too far away, so the parallax can be too small to measure accurately. The smallest parallax that is measurable from the ground is about only 0.01 arc second. Less than that value we cannot measure from that ground. So that is actually sets a limitation to this geometrical method of determining the stellar distances. This means that from the ground, the method of trigonometric parallax has the following limitations, that is, we can measure the parallax up to p is equal to 0.01 arc seconds, then the corresponding distance will be 1 by p, which is equal to 1 by 0.01 arc second, which is equal to 100 pc. So the parallax second we can measure good out to 100 pcla. So if you consider this distance 100 pc, it only gets 10% of the distances that we can see. And also if you consider this distance, only few hundred stars are this close, all other stars are beyond this limit. So this method still has a limitation that it can measure distances up to 100 parsec. So that's all about the distances of distance measurements in stellar astronomy. Now we have to discuss about the brightness of the star, that we will discuss in the next lecture. Thank you.